Live streaming is on.
Hey everybody, welcome to the December 2020 meeting of the Baton Rouge Astronomical Society. Our guest tonight is Dr. Penny with the Louisiana State University, and I'm going to toss it over to Coy for introductions.
All right, good evening, everybody. Thank you for joining us. I would like to introduce Matthew Penny. He's an assistant professor at LSU in the Department of Physics and Astronomy. Tonight, he's going to be talking about MISHAPS, a survey to understand the ingredients of giant planet formation. So everyone, please give him your attention. Thank you.
Okay, thank you for inviting me to give this talk, and good evening. It's nice to meet you, those that I haven't met so far. I'm sure I'll be meeting you in person at some point in the future, hopefully not too far in the future. So yeah, I'm going to talk about some research that I do, in particular a survey called MISHAPS, which is a survey to try and understand what goes into giant planets. So first, I'll start by talking a little bit about myself and my research.
Just a brief moment. If you're still running your PowerPoint, it looks like it has stopped.
Oh, okay. Does that not change?
It was fine a minute ago.
Okay, I'll stop and restart. Let's try this again. Okay, can you see the outline slide?
Yep, I think we've got it now.
Great. Okay. So yes, I'll tell you a little bit about myself and my research. Then we'll talk about how giant planets form, and then go on to the role of metals in the astronomer's sense, and then finally I'll tell you about how we go about searching for planets that might have different amounts of metals in them by looking in different stellar populations. So a little bit about myself. I've taken over teaching of the Astro 7361 course at LSU, so I'm now intimately familiar with the telescopes at HRPO. This semester was my first time teaching it, and it was a lot of fun, but it was also quite a challenge as well in the pandemic, having to work part remote and part in person, and then added to that the power supply to the 20-inch blew up just as we were about to start the semester. But thankfully we were rescued by Greg Guzik and Jill Junot, who cobbled together a solution by cannibalizing the 16-inch to get the 20-inch back in working order. And here on the left is just an example of what some of the images that we took this semester. This is M33, of course, with a small mosaic from the 20-inch. But onto my research. So I work on exoplanets, and in particular exoplanet demographics. So that's kind of a niche field where we aim to study not just individual planets, exoplanets that we find around other stars, but try to understand the whole population of exoplanets that we see. And in particular, one of the main goals of this is to try and understand how planets form by looking at large numbers of them and the general properties of the population, and not just of the individual planets. This diagram that I'm showing here is one of the main diagnostic diagrams we have of the...
if I could stop you really quick again, it seems your video has yet again stopped.
No.
You might try sharing the entire screen instead of just sharing the program, and see if that does a little better.
Yeah, let's try that. My apologies.
It's buggy program at times. I was lamenting that a little earlier.
Yeah,
they're too cheap to get a pay service, and so.
Well, I'm too cheap. Other people wanted one, and to be fair, other people said they would pay for it, and I still refuse because I don't believe that it should be a paid
Yeah.
service.
So hopefully you can see my screen now. Is that right?
We're still seeing your video.
Maybe I turned it off with a double click. Let's try one. Entire screen. Allow. Okay. You should see it now, right?
Now,
Probably
yeah,
changed.
we've got your echo. Yep. Large survey for exoplanet demographics.
Yes. Okay. So you can see that screen with the menagerie.
I'll try and keep you appraised if it kicks out again, or we'll just let you go on politely and just nod as though you know what you're talking about. It's your choice.
Yeah. Please stop me if it happens again, and I'll maybe try doing the presentation outside of full screen, and that might prevent problems.
All right. Please.
So yeah, going back, this plot that you can see is basically tells the picture of exoplanet demographics in one plot. So it's a plot of the mass of all the known exoplanets versus the orbital distance of them, and also plotted on here are the planets in our own solar system for comparison. And so one of the things you'll notice about this plot is that there's a lot of exoplanets. So in the last 25 years or so, we've learned a huge amount about the variety and the abundance of exoplanets. But you'll also notice that it's incomplete, and especially incomplete to planets that are similar to our own solar system planets. They occupy a corner of its diagram that is not that there's only a very small number of exoplanets known that have similar properties. So one of my goals is to try and fill out this diagram so that we can see exoplanets of all types and at all distances from their stars. And so one of the ways you can do that is by using new techniques that can find planets around with different kinds of properties. In particular, there's a technique called gravitational microlensing, which I won't go into the details of because that's not what the talk today is about. But that's a technique that can find planets that are much more distant from their host stars than most of the exoplanets we've found so far. And one of the missions or surveys that we'll use to find this will be carried out by the Nancy Grace Roman Space Telescope, which is a NASA flagship mission on the same kind of scale as the Hubble Space Telescope and the James Webb Space Telescope that will launch in the mid-2020s, so somewhere around 2025, 2026. And I'm involved in plans for a large survey on that mission to basically fill out this entire exoplanet demographics diagram and search for planets of all sizes or all masses around stars at large distances, so that we can find analogs of things like Jupiter, but all the way down to masses as small as Mars, or even as small as Jupiter's largest moons. So that's one aspect of my research. What I'm going to talk about today, though, is a slightly different one, and that's using ground-based telescopes to search not for planets far away from their stars, but for planets very close to them, or hot Jupiters. And in particular, looking for these planets towards the very center of the galaxy, or the Milky Way. And to do this, we're using the Blanco 4-meter telescope down in Chile. So this kind of brings me on to link things back to the exciting events of this week or next. So I'm really excited to see Jupiter and Saturn so close to each other in the coming days. And I put what you're missing, because obviously if you're listening to me, you don't have the opportunity to go out and look at it tonight. But the clouds was spoiling that anyway. So the reason why I'm showing this though is Jupiter and Saturn are they dominate the solar system in terms of they're the largest planets. They account for virtually all of the mass in our solar system, other than the sun, obviously. So understanding where giant planets like Jupiter and Saturn come from, how they form, is critical to understanding basically the entire planet formation process. Depending on how giant planets in a system form, you might get very different outcomes for smaller planets like our own Earth. And so what are Jupiter and Saturn made of? What are giant planets made from? If we take a look at the atmospheres of them, so the surfaces that we see, at the very cloud tops, the makeup of Jupiter's atmosphere is almost entirely hydrogen and helium, with trace amounts of heavier elements. But that's just what we can see on the surface. Buried beneath, where material that's made of heavier elements has typically had time to sink to the core, or may have been what started the formation of the planet itself. Maybe a giant rocky core was what started the formation of Jupiter. So that the makeup of Jupiter itself, the entirety, is less well known. So what we currently believe, and this knowledge has improved vastly in the last few years with the Juno mission that is orbiting Jupiter, is that Jupiter is made up of roughly 70% hydrogen, 23% helium, and then about 6% of heavier elements. Now, 6% doesn't sound like a lot, but if you think about the fact that Jupiter is 300 times the mass of Earth, 6% of that 300 is about 20 Earth masses. So inside of Jupiter is enough rocky, heavy element material to make up all of the terrestrial planets in the solar system. So understanding how that material found itself inside Jupiter and not spread out throughout the solar system in smaller planets is an important thing to understand. And so to get to that, to start to try to answer that question, we have to step back a little bit and think about the planet formation process itself. So we know that planets form out of a disk of gas and dust that surrounded the very young sun just after it was born. And from that disk, inside that disk, heavier elements formed into dust particles. They settled towards the center of the disk and then combined and grew into planets. At least that's one picture for how planets grew. So starting from dust particles and then clumping together into pebbles, asteroids, things the size of a moon, things the size of the Earth, and then growing ever more until they could gather gas. But it's not the only theory for how giant planets might form. So the scenario I've just described is the core accretion scenario. So first you start out with a core of material that then can gather gas or accrete gas onto it to grow up into basically a giant atmosphere that eventually, once the atmosphere grows large enough, will undergo a runaway process and just very rapidly grow into a giant planet. The other possible, or the other competing theory for how giant planets form is rather than bottom up and growing from small things, it's known as the disk instability theory, and this theory relies on having a very massive disk around the protostar that is so massive that it becomes unstable gravitationally, and then the clumps that form in that instability basically rapidly collapse into a giant planet. So one of the goals of exoplanet demographics work is to try and observationally see if we can tell how giant planets formed between these two theories using the observations of planetary systems that we find. I'm guessing that, having not interrupted, you can still see my screen.
Yeah.
Okay, thank you. I'll keep going.
I keep watching for the mouse to move. As long as the mouse is moving, I can see.
So let's review the evidence for and against these two theories: the core accretion theory, where you grow a planet up from small particles, or the disk instability theory, which you basically collapse a cloud of gas into a planet in one go. So one of the critical pieces of evidence supporting the core accretion theory is that the number of giant planets that we see, or the occurrence rate of giant planets around stars, seems to increase with a quantity called metallicity. So what is metallicity? So astronomers have taken spectra of stars for over 100 years now. And from these spectra, you can see the presence of different elements in the atmospheres of the stars. And metallicity is just a quantification of this. This is the most technical slide. I'll pull back in a second, but I think this is important to understand the kind of range of properties that different stars have. And so astronomers are a little weird. So a chemist, if you asked a chemist what the periodic table would look like, they would describe all these different kinds of elements that exist. 118, I think, are known of now. But astronomers, if you asked them to draw a periodic table, most of the time we're just happy knowing about three different things: and the amount of hydrogen, the amount of helium, and then the rest. So anything heavier than hydrogen and helium. This we lump into a quantity, into the term metals, which not all of them are metals, but we're pretty bad at coming up with names for things. So metallicity is basically the amount of metals that a star has. And we measure it relative to our own sun. So if a star has more metals than the sun, then we say it has high metallicity. Less, it's got low metallicity. And we tend to describe it with this weird notation, Fe on H. It's known as, or said. And this is just basically it's a logarithmic scale for metallicity. So it's, if you have a metallicity of -1, it means that the star has 10 times less metals than the sun. If it has a metallicity of 0, it's the same as the sun. And plus a positive number means it has more metals than the sun. So, okay, now with metallicity described, let's go back to this diagram. So what this is showing is the percentage of stars that have planets as a function of their metallicity. So towards the end of the 90s, it was noticed that that stars that had giant planets tended to have higher metallicities. And then in the mid 2000s, this was properly quantified statistically. in this exact diagram. And this is known as the planet metallicity correlation. And basically it says that the more metals a star has, the more giant planets it tends to have. So if you increase if a star has twice the amount of metals, heavier elements than the sun does, then the number of planets it has increases by the chance of it having a giant planet increases by about a factor of 4. So the reason why this is a key piece of evidence in support of the core accretion theory is that I basically described the process by which a giant planet might form a couple of slides ago, but the process by kind of dividing up this process, you would start by forming a core of things like rock or ice, which are made up of elements that aren't hydrogen and helium, so are metals. And so you'd start by growing a core, and then once that core was massive enough, you would start to gather gas to that core. And once the amount of gas in the planet was more massive than the total amount of heavier elements, then you would expect the planet to rapidly accrete all of the gas from the disk surrounding it, until the point at which the planet has swallowed up all the gas that's nearby and opened up a gap in the protoplanetary disk. So this is a nice feature, a nice kind of picture of how a giant planet might form. But one problem is the processes involved are quite slow. So this is a plot of the growth of the planet, the mass of a planet, as a function of time. And so it might take a few 100,000 years to grow a core to be massive enough to start to significantly accrete gas. But then once you've got that core, it will then take millions of years to gather enough gas to undergo this runaway accretion phase. And so that's fine, but the trouble is, from observations of protoplanetary disks around young stars, we know that the typical lifetime of those disks is only, on average, about 3 million years. So the theory of core accretion says that you'd expect giant planets to grow like this, but they wouldn't grow fast enough to reach a stage where they undergo this runaway accretion and finally reach a mass of Jupiter. Okay, so that's one of the problems. How about disk instability if core accretion doesn't work? The evidence for this is that we see a number of planets very far from some very massive stars. So in this case, this is HD 8799, which is a system of 4 giant planets around a massive star, very far away from the star. So the scale bar here is 20 astronomical units, which is 20 times the distance the Earth is from the sun. And so there's giant planets more massive than Jupiter at distances that are hundreds of AU from its star. And this is kind of exactly what you'd expect to see in the disk instability scenario for planet formation. You need a very massive disk, which probably implies that you need a massive star to begin with for this disk to undergo instability and fragment into smaller objects like the giant planets. So we see some systems that look like they formed this way, but they're very rare. So the theory requires that the disk that they form from is very massive, and then we know that massive stars that would have such massive disks are rare, and indeed we only see a very small number of those massive stars have planetary systems like this. So it looks like disk instability could form some planets, but it's not going to explain all of the giant planets that we see, and especially giant planets at distances of Jupiter and closer. So, okay, let's come back to what the planets are made of, and see if we can gain any clues from that. So, as a reminder, we think that Jupiter itself in bulk is made up of roughly 6% of heavier elements. And so is it just, so I've mentioned that there's this correlation between the occurrence rate of giant planets and metallicity. Do we see this in other planets? So smaller rocky planets where you definitely expect to see that kind of effect. And so there do indeed, so this plot is showing the occurrence rate of planets in high metallicity stars versus the occurrence rate of planets in lower metallicity stars. And so for smaller planets, you do see an enhancement in the number of planets around higher metallicity stars, but it's nowhere near the enhancement that you would that you see for gas giant planets. So this is another element or another piece of evidence pointing to the fact that maybe it is the cores that are important. And if you're confused at this point between the two different theories, that's okay. This is still an open question. We don't know the answer, and this is what we're trying to get at. So, okay, let's take a look at how we can solve the problem of the core accretion taking so long that the disk that the planets form from dissipates before the giant planet can form. And so to understand this, we need to look at the structure of the protoplanetary disk. And in particular, one of the main features that we believe actually exists in such disks is known as the ice line. This is an imaginary point where the temperature in the disk is cool enough for molecular species like water or carbon monoxide to freeze out. So they go from being in a gaseous form close in to being in an icy form further out. And so if you, at this ice line, we expect the amount of solid material in the disk to rapidly jump as you go from inside to outside the ice line. So inside, the only solid material in the disk we expect is rocky stuff like silicon dioxide, stuff that makes up sand, that kind of material. But once you get far enough away from the star that the disk is cooler, you start to form ices, and then you get much more material that is in solid form that could potentially stick together and form the core of a gas giant planet. And if you have more material, it means you can form a core more quickly, and then you might be able to form a core quick enough to start accreting gas before the gas dissipates as the forming star basically heats up and blows the disk away over time. So okay, why might this be important? So I've mentioned that astronomers talk about metallicity mostly by lumping it together, all the heavier elements together. But that's not always what we do. We can see in the spectrum of stars, we can see individual spectral lines from different types of elements. The reason why we measure metallicity with this quantity FE(H) is that iron is one of the most prominent lines in the spectrum of a star. So this here is the spectrum of the sun. So basically the light at different wavelengths spread out. And we see the darkest bands here are due to absorption of light by iron. And so that's the main tracer of total metallicity. But we can see different lines from different elements, and so we can, if we look more carefully, we can count, basically look at how much of each different element there is relative to the others. And so so why this? Okay, sorry, I'll step back 1 second. So stepping back to the question of planet formation, if metals are important for forming planets, what metals are the most important? That's a question that we might want to answer if we're going to understand how it is that giant planets form. And so to do this, we need to look at stars that have different ratios of the different different elements, and see if there's one of these elements that might cause more of it, might be more abundant in planets that host giant stars than others. The trouble is, because of the way that stars form, and in particular the origin of all these different elements, they form. It means that the amount of different elements that given stars have is actually pretty correlated. So if a star has more iron than the sun, there's a good chance it has more of every other element as well. And this is because starting from the Big Bang, most of the universe was just made up of hydrogen and helium, and then virtually all of the rest of the elements in the universe were formed in stars themselves through the process of nuclear fusion. And then they get those elements, so things like carbon, nitrogen, oxygen, relatively light elements, were fused in the cores of stars, and then when those stars exploded, they were spread to the rest of the galaxy, and then a second generation of stars could form with more of those heavier elements. And the long story short, different types of stellar explosion, release different types of elements, or different more massive stars can form heavier elements than less massive stars. And so more massive stars live shorter lives and explode relatively quickly. And so very quickly you build up lots of elements like iron and cobalt, things like that. Sorry, I'm getting this mixed up. Sorry, exploding massive stars form basically the whole range of elements. So they form, they build up elements one at a time. So go to carbon, nitrogen, oxygen, gradually getting to heavier elements. So the massive stars, when they explode, they will spread all types of elements out into the universe relatively quickly. But the most heavy elements, including iron, cobalt, etc. Those require a different kind of explosion to be formed. Those require a type 1a supernova, which is caused by a white dwarf exploding, either by accreting material from a donor star or by two white dwarfs colliding. And so the heaviest elements, and in particular iron, only gets formed relatively late on because you form white dwarfs from lower mass stars which live for longer, and so it takes longer to form these elements in large quantities. And so all this means is that in the local, so in the region of the galaxy where the sun lives, we have stars that all have basically a strong correlation between the amount of iron they have and the amount of other elements, so things like oxygen. To find stars that have higher levels of oxygen relative to iron, we need to go to different populations of stars that formed in a different way, or had a star formation history that differed to that of the population of stars to which the sun belongs. Okay, so where might we find in the galaxy a set of stars that has a different set of chemical elements to those that we have in the sun and the local stellar population? So we live. The sun is part of what's known as the galactic thin disk. So the Milky Way is a disk galaxy. The sun lives about halfway out towards the edge in the disk of the galaxy. So this is the Milky Way that we see in the sky is pretty much a thin line. This is the thin disk of the galaxy. And so all of these stars in the thin disk have a similar star formation history, and so have a similar chemical composition as well. There are two other major populations in large numbers that are potentially accessible that we could search for stars, though. There is the galactic thick disk, which is just a thicker population of stars. So these are older stars that formed in a burst relatively quickly. These have more oxygen and magnesium elements like that than the sun does, or than thick disk stars do at a fixed amount of iron. But the thin disk stars tend to have relatively low metallicities, and so we don't expect them to have very many giant stars. What we'd really like is a set of stars that have higher metallicities, but also have a different chemical composition than the sun does. And so for that, we can go to the galactic bulge. And so this is a population of stars surrounding the center of the galaxy. So if you look up at the Milky Way, and in the summer in particular, you can see that the center of the Milky Way is significantly. It's thicker than the disk of the rest of the Milky Way, which is the disk. So the very center, we're seeing towards the bulge of the galaxy, where there's basically a almost spherical population of stars. It's not quite spherical, it's actually more bar-like, but generally it has a much higher distribution than the disk of the star does, disk of the galaxy does. So this population actually has exactly what we want to look for. It has high metallicity stars, so there's a high probability that there are giant planets around galactic bulge stars, but also they have high abundances of oxygen. And okay, oxygen, why is that important? Oxygen is, of course, a key component of water, H2O. And so if you have more oxygen, you can form more water. And that means once past the ice line of a star, you will then have much more water ice. And so if you've got more water ice, you have more solids, you can potentially build up a giant planet core quicker still than you can around high metallicity stars in the galactic disk. So what we might expect to see then is that that stars in the galactic bulge would be expected to have higher numbers of giant planets than stars nearby, stars in the thin disk. So how might we go about finding stars in the galactic bulge? So you might be familiar with the Kepler exoplanet survey. So this was a survey for exoplanets, but looked for them by waiting for a planet to pass in front of their star. This is known as the transit method. So the planet transits in front of a star. If we want to look for, so Kepler looked at for planets around stars in the galactic disk, relatively nearby to the sun. If we want to look for planets around stars in the galactic bulge, we're looking further away, so the stars are fainter. In fact, they're about 100 times fainter than the stars Kepler looked at. You also might be familiar with TESS, which is a smaller satellite, but it's doing similar work to Kepler, but doing it for the entire sky. The stars in the bulge are 10,000 times fainter than those that TESS looks at for planets. And in addition, because it's the center of the galaxy, there are many, many more stars there. And because they're so far away, all those stars are crowded together as well. So we face a significant challenge if we're to try and search for planets around those stars in the bulge. But this is precisely what we're trying to do with the MISHAPS survey. So MISHAPS stands for the Multiband Imaging Survey for High Alpha Planets. And this is a survey we're conducting with the 4-meter Blanco telescope at the Cerro Tololo Inter-American Observatory in Chile. And mounted onto this telescope is the giant 520 megapixel dark energy camera that covers an area of about 3 square degrees. And we've been awarded 38 nights on this telescope over the course of 3 years to search for planets in the galactic bulge. We expect to detect around 400 of them, and the observations for this started in 2019. Of course, you should be careful what you name your survey. Turns out that when I was observing on the first observing run for the survey, a mishap did occur. It's not quite as bad as it looks here. This is me lying on the ground in the dome of the telescope. I had an attack of stomach acid that had similar symptoms to a heart attack. So it basically worried everyone on the mountain. They called the medical professionals and took me down away from the telescope in an ambulance. It was all fine. I recovered pretty quickly before I even left, but they insisted I went down to the hospital to be checked out, and thankfully got back in time to see the solar eclipse that took place in July last year, the following day. Coincidentally, there was another solar eclipse in Chile today, which unfortunately didn't get to travel to go and see, but this one thankfully I did. So there I am on the left. So okay, going back to the survey. So we're using this giant 500 megapixel camera. We're taking images of a single field in the center of a galaxy or near the center of a galaxy every 3 minutes. And in that giant field, we're monitoring 6 million stars to watch for planets passing in front of them. But because giant planets very close to their stars are relatively rare, we only expect 1 in 10,000 of these to have a transiting giant planet that we can detect. But here is the kind of data that we've started gathering. So this is unfortunately not a giant planet, but it's the kind of signals that we're expecting to see. This is a plot of brightness against time, and so you have a star that stays constant for a while and then fades for a brief period of time before getting brighter again. This is too deep to be an exoplanet, but it could be it's most likely another star passing in front of a brighter star. But we do see in our preliminary searches through the data, we do see some cases where it looks very much like a planet. The dip in brightness is only about 1% or so. And we have, even though these stars are so far away, we were talking before the talk about the faintest stars that you're looking at. These are magnitude 19 and 20 stars. So they're extremely faint, and that's why we need this giant 4-meter telescope to search for them. But here is an example of one such candidate, the first one that we found. And I should mention a lot of its work now is being done by Ali Crisp, who's an LSU graduate student working with me. And she's working on improving the pipeline that we use to measure the brightness and search for these planets. There's more that you can do with this data. You can search for variable stars. Here's an example of what I think is an RLIRE, but please tell me if I'm wrong. In the Galactic Bulge, and we're also, because we're monitoring the same field continuously, we also see tons of asteroids pass in front of the field as well. And because we're having to look for such small events on such faint stars, we actually have quite a deep sensitivity to asteroids. And so an undergrad, Mars Newman, has been at LSU, has been working with me to search for those asteroids in the data. And they've found literally hundreds of them, and basically done an amazing amount of work to just visually identify them, in the hopes that we can then use new machine learning techniques to search for these automatically. And here is an example of one of those asteroids where the asteroid is moving, and the different color channels in this image are different points in time. And basically this is a stack of images that have then been subtracted, another image has been subtracted from them, and so only things that vary or move are left in these images. And so Mars has been visually looking through these images with lots of artifacts to find the real objects that are moving. And so, okay, that's basically that's the project. It's still very much new. We've collected 7 nights out of the 38 that we've been allocated, so there's another month of observations to go. The pandemic has obviously delayed us. It's like we've lost a year of observations, but they'll be given back to us at a future date. But it, of course, delays the results that we expect to get. We're processing the data well. We reach the sensitivity we need to find planets. And as I've shown, we've got some candidates already. But the full number of 400 planets that we expect will require the full data set. And I guess at this point, so that's pretty much done, but I should acknowledge the support that we've received for this project from the Louisiana border regions that have basically paying for Ali's graduate work. So, okay, that's my talk. I will leave on one slide. If this was not enough astronomy talks, later in the week, Astronomy on Tap on Thursday is having another one of their monthly events, where there's a talk on a relatively similar topic, lithium synthesis in stars, so building up elements in stars. But if you're fed up with astronomy, there's also a talk about dinosaurs. So thank you for listening, and sorry if I went a little long.
Oh no, you didn't go long. We yammered on for the first 10, 15 minutes, and then there was yeah, you're perfectly fine. Thank you very much for the talk. I'm going to try and remember how we stopped your screen earlier in the day so we can get back to
I can manually stop it.
Okay.
There we go.
There we go. Yeah, I wasn't quite sure how I think we kicked the other fellow out, and I'd rather not kick you out if it's all the same. I think some people might have some questions. As much as you might love to give a talk and then bounce without having to field any questions, I'm sure if you had known that was the case, you probably would have thrown in some bald-faced lies just for good measure in the process.
No, I love taking questions. It's the best part of giving talks.
Yeah, I've felt that you sort of lost yourself in part of the talk, and I think you're very much accustomed to having people interrupt you in the middle of the talk.
Yeah, I meant to say please interrupt if I'm I've forgotten to mention something.
But yeah, I thought it was a very informative talk. I thought it was. I'm still a little bit confused on how the difference between the accretion method and the
disk instability.
Like it seems like in both cases you're going to be forming the planets around a solid core, and basically the difference is on how that first little solid core develops. Is that about right?
Maybe I didn't explain that very well in the disk.
Well, I'm slow too.
No. So no, it's a process that it's a hydrodynamic process. So it's basically, so what I mean by that is so disk instability happens when you have a fluid or a gas that is unstable to gravitational collapse. So if you have a massive star that has itself a massive disk, so a lot of material around it, if the density of that disk reaches a certain point, then it can essentially just spontaneously collapse and fragment into different clumps. So there's nothing at the center in the disk instability case. It's just there was enough gas that happened to accumulate at a certain point, and then it starts collapsing under its own gravity.
Okay. That clears things up a little bit. Okay. Yeah. I'm so used to thinking of Jupiter as being a ball of gas that the idea that there's a solid core in it is kind of not quite. And so that brought up the question as well, do all these guys start off as giant cores? So actually, yeah, the idea of a core instability is more in tune with my initial interpretation, that it was just like this gas that its own little gravity sort of pulled it into a sphere, rather than, sort of accreting gradually over the course of hundreds of millions of years around a solid object.
Yeah, and the time scale for the disk instability collapse is incredibly short. It can be hundreds of years. Yeah. So, sounds like long for us, but in astronomical.
Yeah, under the other thing, the other way of doing it sounds like every planet starts off as like a solid rocky type core, and just Earth is a failed Jupiter, that sort of thing.
Yeah.
Or we've got a lot of gas, it's just nowhere near enough.
Yeah, exactly.
And the other one seems more in tune with, oddly enough, my initial introduction to the gas giants. So I'm a little bit better with that. And thinking of it kind of like you're going for a paddle in the lake or whatnot, and you create a little eddy, and it forms its own little system off, and something like that. That's
that's exactly the kind of thing that would happen.
Yeah. Okay, great. Questions?
My name's Thomas, and I was wondering something. You had said, Dr. Penny, that a lot of the planets that we're looking for are towards the center of the Milky Way, and that's where we find a lot of oxygen. And it makes me wonder, since we're not at the center, does that mean we're an outlier?
That's a good question. So, in terms of the number of stars in each population, I think there's probably similar quantities of stars in the disk compared to the bulge. Maybe the bulge has fewer stars. I should know this. I've forgotten at this point. But they're not. The sun is not that much of an outlier in that case. It's pretty average in terms of stars in the disk, and there's lots of disk stars as well.
Cool.
Usually with these talks, I end up having a question about, well, where do we go from here? So once you gather the data, I'm sure you've got your own plans for what we're going to do. I'm looking bigger picture. Could we take your data and then apply models to look at accretion versus instability and sort of rewind and then fast forward, test the models?
Yeah, so that's basically the idea is that I'm trying to find something that is, or we're trying to find, I should say, it's a group effort. We're trying to basically make a measurement that's a target for theorists to aim at. So one thing I forgot to mention basically is, and it's kind of a key point, so I really should have mentioned it, is that if we do find, so we're trying to make a measurement of the fraction of stars that have giant planets in the bulge relative to the fraction of giant planets in the disk. And from that, we'll infer that if we see the same fraction, then it would imply that elements like oxygen actually aren't that important. So it would disprove the hypothesis that I kind of presented. But if there are many more planets in the bulge per star than there are in the disk, then that would suggest that elements like oxygen or any of the other elements that kind of go along with it are important for planet formation. It doesn't necessarily say that that's definitely the case, and it's not at all obvious what the mechanism is. Just this picture of the snow line seems to be an intuitive way to cause it. So that's a kind of very simple theory that we've tried to aim at when designing the survey, but it will be a whole can of worms if whatever we find, whether there are more or whether there aren't. We'll have learned something, but not enough to disprove one theory either way. Just have the theorists have more things that they need to explain.
Yes, Chris, I have a question. I've seen a lot of examples of the solar system we found on exoplanets, and there doesn't seem to be a single one that's even remotely like ours. Most
Yeah,
I've seen are very, very different from us. Has they ever found one that's even close to ours?
so we are just about reaching the capabilities to find analogs. So the problem is, for most of the techniques you use to find exoplanets, you're relying on the orbit of the planet to be able to find it. So you either use the transit method, in which case you want to see the planet go around a few times to be sure that it's the same planet. And so the further away planets are, the longer that takes. And so we've just not been observing long enough to find them. And it's the same with the radial velocity technique, which rather than watching the planet go in front of the star, you watch the motion of the star caused by the mass of the planet as it orbits. And again, that you need it to complete a full orbit, or probably two or more, to be confident that there's a planet there. So we just haven't. So Jupiter orbits in 5 years, Jupiter in 10 years, Saturn in 30 years. So we've just not been measuring at the sensitivity you need to find like full analogs of the solar system. And then even worse, if you add, especially with the radial velocity technique, you're looking at a continuous signal that's varying. Once you start to add 2 or more of those signals at the same time, you need to go kind of one period times the other period as long to disentangle them. So we've not really had much of a chance to find solar system analogs that have Jupiters and Saturns like ours. Then added to that, the Earth is actually incredibly small, and is really difficult to find. So most stars that we've looked for, we just don't have the sensitivity. There is one, so I should say there are now, radial velocity searches have now found planets with 30-year orbits that are about the mass of Jupiter or so. So we're starting to be able to see systems like the Sun with those observations. One system where we have seen an analog of Jupiter and Saturn, and then the gravitational influence of the planets causes light from the background star to bend and be magnified. And so if the path of the background star relative to the foreground star is just right, you'll get the planets lining up. You'll see signatures from multiple planets in the system. And so there's one we've seen where it's a planet, a pair of planets roughly at the same ratio of distances, roughly at the same ratio of masses to Jupiter and Saturn. But it's around a star that's half the mass of the Sun, and so it's half a Jupiter mass, half a Saturn mass for the planet.
I don't know, what always fascinates me is that we're catching these solar systems in different phases of evolution as well. I mean, we look, we see different sizes, but we don't think about, well, these are in this phase of formation. Some, I'm sure, still have that protoplanetary disk phase going on. There's still that junk flying around.
Yeah, there's, I didn't mention age, or other than the formation process, I didn't mention the other things that can go on. So we, planetary systems, if you have more than one planet, are chaotic. And so those can cause orbits to be rearranged, planets to be ejected, things like that. And some of it will happen quickly, but some of it can take billions of years to just reach the right conditions for chaos to ensue. And yeah, there's a huge variety of things. Another thing that, another recent discovery last year was a planet orbiting a white dwarf that spent some time orbiting inside the star and managed to survive. There's in terms of demographics, you try and simplify it down to just the big picture and try not to focus on those individuals, but there's so many cases that are fascinating in their own right. But it's, the amount of variety is amazing and kind of scary when you think about our own formation and what needed to go right for us to be here.
If you don't mind me asking another question, you're looking at the Milky Way, and I was wondering if it's all right to ask where the images for the Milky Way are coming from, and this may just a little bit of a softball question, but I think it's relevant to ask, given that, and God bless you, literally, you're in the Baton Rouge area. To what degree, if any, has light pollution inhibited your efforts?
That's a good question. So, as I mentioned, we're doing these observations from kind of professional sites that are picked for being the best places in the world. So that's, in this case, it's from Chile, which is in the southern hemisphere, which is ideal for seeing the Galactic Bulge, which is at 30 degrees south. But yeah, light pollution is still a problem. So, and it's a challenging. It's not a simple problem either, because many observatories, especially those in the southern hemisphere, Chile's doing okay as a country, but it's still developing. It's not at the level of development that the US is, and so the economy there is growing. There are towns and cities within 100 kilometers or so of the mountaintops that you want to grow economically, and with that comes more light pollution. But of course, it harms the observations we do. So yeah, it's a problem. It's getting worse over time, but I think there are lessons to be learned, because I know that Chile recognizes the importance of its observatories, and so I think the nearby cities have tried to install better lighting for light pollution. But if that comes at a cost and Chile's not flush with money, it's something that basically all of those concerned need to be involved with. Like, maybe if we want to preserve those sites, we need to fund them better and help provide some help for these solutions.
Amen.
I got a question for you. Has the massive proliferation of the low orbit satellites like Starlink, has that started to impact y'all down there?
Yes.
More are going to be launched.
Yeah, so it's a big worry. So like, to the naked eye, the Starlink satellites, I've seen the trains passing over, and they're an amazing sight. But yeah, when one of those goes through your your field of view, with these projects with giant cameras like this, the fields of view are pretty big, so it happens. Yeah, we lose certain numbers of images to them, which it's not all of them, it's not the majority, but it comes at a cost. And I think once the constellations are at 20,000 or so satellites, there's almost always going to be one in your field of view. There's only 60,000, is it, square degrees? So basically you're guaranteed to have one there.
I think I read somewhere that within 20 or 30 years, you won't even be able to take binoculars to the sky without having it crawling with the satellites.
Yeah, it's a worry.
Kind of scary.
Well, they say that we're saying that the light pollution by 2040 will be so bad that any metropolitan area, you'll only be able to see 3 to 4 of the brightest stars. That's all you'll ever be able to see in the sky.
Well, but the point being is that with the satellites, you can't get away from them. And you would have to launch your observatory outside of the orbit of the satellites, so that there's no more retreat to the country. Or I think the closest thing is there's talk of putting a giant telescope on the moon now. There's every once in a while you read something about them filling a giant crater with liquid metal or something like that. It sounds absurd, but it's really cool. But yeah, that's why it sounds absurd.
Yeah. Well, space telescopes are great. I work on them, but they're so expensive that you just can't replace what's on the ground. You can do you can do so much more with a number of small telescopes than you can do with just one. They can do different things. Like the space telescopes can do things you can't do from the ground, but you can only look at so much of the sky with them. So you need things on the ground too.
Well, that, and they're a real pain to refuel after a couple of years. No, oddly enough, they were originally designed. I think Hubble was originally designed to be refueled and maintained, but then the old pickup truck broke down, and
I think the first designs had human observers there too.
Really,
I
didn't know that one. Wow, yeah. You think it's lonely on a mountaintop for a week's day? I'm sure there would still be no shortage of people volunteering either. No.
Yeah.
All right. Any more questions for our esteemed guest? Preferably about an object of his expertise and not just in
I don't
general.
know. You can try and stump me if you like.
All right. So a train moving at 30 miles an hour leaving Pittsburgh. No, I seriously doubt I could stump you. I could stall you, but I could not stump you. That is my belief.
No, I'm. You can very quickly get out of my area of expertise.
Well, and why would we want to? It's been such an engrossing talk, and you're doing very cool work that really, when you think about the types of things that you see on the national television and the magazines, that's always the talk of black holes, the talk of gravitational waves, and the talk of exoplanets. And so yeah, it's not only an interesting area of study, it's insanely popular as well. The only thing more than that is how Mars is going to look the size of the moon in a couple of years, which we have to deal with all the time. All right. So if there are no further questions, we'll thank Dr. Perry for his time, and also he will be around the observatory for the next couple of years, we hope, when he's teaching his courses. So when we are allowed back in the observatory, you might recognize his face if you see him in the hallways, and you can always pull him aside. If you think of a question later, you can pull him aside and ask him in person, is my guess. And he's a reason. I've met him a couple of times. He's a reasonably nice guy. He'll
Reasonably.
Recently. He hasn't hit me yet. Which is saying a lot if you know me.
As I say,
right.
I look forward to meeting you all in person at some point, in hopefully the near future.
Well, that's lovely. Thank you very much for your talk. It was very great.
Thank you.
Thank you, thank you.
Maybe said thank you.
In the dog's like.
Dog approved. Okay. And with that having been said, we're going to allow you to dismiss you and allow you to continue on with your night and any which way you see fit while we finish up our meeting, unless you want to stick around for the normal types of talks that go on to these types of meetings.
The real exciting stuff.
Yeah, the really exciting stuff.
I'm sure I will join in the future, but I haven't eaten dinner yet, so.
Then by all means, go enjoy your dinner or not, as is your want. And again, thank you very much for your talk.
Thank you again.
No problem.
Yes, thank you.
Thanks for listening. Bye.
And that concludes our public portion of our meeting for